Hello, you may have noticed that there are two videos for Chapter 2, Section 4. That's because this section has a lot of information, so I've broken the videos down into two. There's a break in the middle to indicate where Part 2 starts, so I urge you to take a break between them as there are a lot of notation and formulas introduced in this section, and it can get a bit overwhelming. Make sure you're noting all the symbols and formulas somewhere and keeping up with the lecture notes. Pause the video where you need to in order to stay on track. Okay, prepare yourself for some work. You can do it. I believe in you. Okay, let's get to it. Welcome to the Chapter 2, Section 4, Part 1 lecture video, Measures of Variation. This section is split into two parts because it contains a lot of information. Let's get started with the first part. In the last video, we talked about how to characterize a dataset's measure of center and its shape, and we made some observations about how the location of a distribution's center reflects the shape of a distribution. Remember we talked about skewed data sets? But one thing we haven't formally discussed yet are the various methods used to describe the variation or spread of data values in a set. So that's going to be our next task. In this section, we're going to discuss how to find the range of a data set, how to find the variance and standard deviation of a population and of a sample, how to use the empirical rule and Chebyshev's theorem to interpret standard deviation, how to approximate the sample standard deviation for group data, and how to use the coefficient of variation to compare variation in different data sets. Let's begin. The range is definitely the most rudimentary of the measurements when it comes to describing the spread of a data set. It's the difference between the maximum and minimum data entries in the set, and the data must be quantitative to use it. It is found by subtracting the minimum data entry from the maximum data entry. Here's an example. Two corporations each hired 10 graduates. The starting salaries for each graduate are shown. Find the range of the starting salaries for Corporation A and for Corporation B. Pause the video and find the range for these two data sets. Okay, let's focus on Corporation A first, and be sure to note that the values in our data set are to be interpreted in thousands of dollars. Ordering the data set helps to find the smallest and largest salaries. It looks like the smallest salary is $47,000 and the largest is $57,000. The range is found by subtracting the smallest, 47, from the largest, 57. Our result is 10. This means the range of starting salaries for Corporation A is 10 or 10,000. Let's compare that to Corporation B. The smallest value for Corporation B is 33, and the largest is 68. So when we find the difference between them, we find that the range for Corporation B is 35, which means the range of the starting salaries for Corporation B is 35 or 35,000. Interestingly, both data sets have the same mean of 51.5 and a median of 51, but they have different ranges. This difference shows in their distribution appearance quite a bit. Notice that Corporation A only has data in the middle of the data values, whereas Corporation B's data covers the entire field. Corporation B's range is larger, so it has a larger spread. What about if the two sets have the same range, but have different means and other characteristics? Pause the video and find the ranges for Corporation C and Corporation D. We see that Corporation C's lowest value is 48, and its highest value is 58, so its range is 10 or 10,000. When we look at Corporation D, its lowest value is 48, and its highest value is 58 also, so its range is the same, 10 or 10,000. Let's see what the distribution looks like for each of them. Now the graphs look very different, even though the data sets have the same range. The graph of Corporation C is bimodal, with a gap between the two separate peaks. Corporation D is a normal distribution and symmetric. The problem is that just calculating the range doesn't really give us a complete picture as to how the data entries themselves are spread out in relation to each other. The only thing the range gives us is a total distance between the lowest and highest values. It doesn't tell us how the entries are situated in between. We need a way of measuring the spread of data that uses all the entries. So when finding the range is not enough, there are other tools that can be used to evaluate the data's variation. The measures of spread that do this, using all the data points in their calculation, are called the variance and the standard deviation. To develop their formulas, we need something called the deviation. The deviation is the difference between the data entry x and the mean of the data set. If the data set is the entire population, the deviation would look something like this. Deviation of x equals x minus mu. Remember that mu symbol? That means population mean. If the data set is a subset of the population or a sample data set, deviation looks like this. Deviation of x equals x minus x bar. Notation, notation, notation. It's very important to keep straight whether you're working with population data or sample data, because the formulas for some of them have distinct differences. In this case, you're using different numbers, the mu, or population mean, or the x bar, the sample mean. In some cases, the formula itself will look quite different. In this situation, it's the same operation. You subtract the mean of the data set from x. A little red flag should be popping up in your minds here. The operation of subtraction is not commutative. The order of this subtraction is important. It's x minus the mean. The deviation can be negative. Our goal here is to measure the overall spread of data. That gives us a better idea of what the range tells us, and that uses all the data entries. You might be thinking that we could use all these numbers to come up with some sort of average to describe the variation, and you'd be right on track. But we can't use the actual average of the deviations because they have the unfortunate characteristic that when added together they equal 0. Think about it. If you find the difference between all the numbers and the mean, you're finding the differences of all the smaller numbers, which will give you negative numbers, and the differences of all the larger numbers, which will give you positive numbers. And as it happens, these all cancel each other out when you add them together. So the mathematicians have decided on a way for this number to still be useful. There's just an extra step that needs to be performed after finding the deviations, and that is to square them. What happens when you square a negative number? It becomes a positive number. So yay, we win. We get to use all of the numbers, and they still reflect the proportional distance between the mean and each data point. Okay, let's see how that works. Squaring all of the deviations and then adding them together has a special name called the sum of squares, denoted as SS sub x, and looks like this. We have a sum that we use to represent the average distance from center. Once you have that sum, you divide it by the number of entries in the population, or capital N. That gives you the population variance. This is denoted by the lowercase sigma squared. There's a problem at this point because the units of measure for the spread are squared units, which doesn't really match the units of the data set itself. So we take the square root. This value is called the population standard deviation and is denoted by the lowercase Greek letter sigma. Remember, sigma squared is population variance. Sigma is population standard deviation. Okay, we've seemed to have jumped quite a few steps in complexity, going from talking about the range, which is just the difference between the maximum and minimum data points, to finding the square root of the sum of the squares of deviations of every single data point divided by the number in the population. Wow. Okay, so let's put it in perspective. You've actually worked with a formula similar to this one in the past. Think about the distance formula. It's the sum of the squares of two differences. That's close to what we're doing, because even if you can't tell precisely from the notation, we're taking the sum of all of the differences between the data points and the mean, or the deviations, squared, not just one, then dividing that whole sum by the number in the population, and then taking the square root. So don't be overwhelmed. You've tackled something similar before. So I want to go over to the process with you one more time. Then we will do an example. Let's look at this both in words and in symbols. To find the standard deviation, we first have to find the mean of the population set, called mu. Then we want to find the deviation of each entry. If you're taking notes, you may want to triple underline that word each. Third, we square each deviation. Fourth, we get the sum of the squares. Remember, this is called the sum of squares, denoted as SS sub x. Next, we divide by capital N the size of the population. This is denoted by sigma squared. And lastly, we find the square root to get the population standard deviation, denoted by sigma. Let's reuse the data set from Salaries of Corporation A from earlier. Find the population variance and standard deviation of the starting salaries for Corporation A listed in the first example. Now you may be wondering if this is a population or a sample, and good for you for remembering to be careful of that. But yes, even though the set is small, this is a population, so we should use the proper notation for a population set. For this data set, capital N equals 10, so the mean mu adds up all the starting salaries and divides that number by 10. As stated earlier, the mean of this data set is 51.5, which is interpreted as 51,500. Remember, we have to calculate the mean first because it goes in the numerator of our formula for population standard deviation. Now that we've got the mean, subtract it from each of the data points to give us the deviation for each point. Recall that it's okay and expected for some of these deviations to be negative. Also note something that we talked about earlier, that the sum of those differences or deviations is 0. That's why we're doing the next step. Next, we square the deviations. When you are doing these calculations in your calculator, be sure you're using parentheses around negative values so that it will square correctly. If you do a little experiment where you try to square a negative number without parentheses, you'll see that you might get a very different result. The correct way to do it is with parentheses. It's a good habit to form. That way you are squaring the negative as well, because as you know, multiplying a negative by a negative should give you a positive. So make sure you're using those parentheses. Next, we add up this rightmost column. This becomes the numerator of our fraction. We divide by capital N, or 10, then we take the square root. Population variance is about 8.9, and sigma, the population standard deviation, is about 3.0. It measures the average distance that any one data value lies from the dataset's measure of center, which in this case, since all these values are interpreted in thousands, is about 3,000. Now, before we go any further, let's make some observations about what we've learned. Number 1, the standard deviation measures the variation of the dataset about the mean and has the same units of measure as the dataset. Number 2, the standard deviation is always greater than or equal to 0. When sigma equals 0, the dataset has no variation and all entries have the same value. Number 3, as the entries get further from the mean, that is, more spread out, the value of sigma increases. The main point being the standard deviation is a measure of dispersion, or how widely spread the data is from the mean. We're thinking about this value as an average distance from the center. You have probably noticed that we've been working with population, and we made a big deal about distinguishing between population and sample data sets. Now we're going to shift over to look at sample variance and sample standard deviation, and I want you to note that there are a few differences to our formula when working with a sample data set. To find sample variance, all the deviations must reference the sample mean, or x-bar, and we divide the sum of squares by the sample minus 1. Taking the square root of this gives us the sample standard deviation, which we denote with a lowercase s. Not a whole lot changes, but you want to make sure you're paying attention to what the problem is giving you. If the context is dealing with a sample, you want to use this slightly different formula and use the x-bar value and divide by the sample size minus 1, as opposed to using mu and dividing by the population size, capital N. Let's look at an example. In a study of high school football players who sustained concussions, researchers placed the players in 2 groups. Players that recovered from their concussions in 14 days or less were placed in Group 1. Those that took more than 14 days were placed in Group 2. The recovery times in days for Group 1 are listed below. Find the sample variance and standard deviation of the recovery times. I'd like you to watch as I go through the process of doing these steps as we did before. Then I will give you instructions on how to do this with your calculator, and I'll want you to work this example with your calculator on your own. Let's get started. First, we need to find the sample mean, or x-bar. We do this by finding the sum of the data values, then dividing by the sample size. In this case, that means dividing 90 by 12. We get 7.5 as our sample mean. Next, we need to find the standard deviation for each data entry S. This is found by subtracting x-bar from each data value. Remember, you will get some negative numbers during this process. Next, we find the squares of each deviation, and finally, the sum of the squares of SS sub x. For this data set, our sample size, or lowercase n, is 12. Our mean, or x-bar, is 7.5, and the sum of squares is 51. To calculate s squared and s, note that n minus 1 equals 11. Now we plug in our formula. We divide 51 by 11 and get approximately 4.6 for our sample variance. Then take the square root of that and get about 2.2. This means that the sample variance is about 4.6 and the sample standard deviation is about 2.2 days. Let's quickly review the steps, then I'll show you how to do this much more easily on your TI-84 calculator. First, we find the mean of the sample data set. Second, we find the deviation of each entry, or subtract the mean from the data value. Next, we square each deviation. Fourth, we add to get the sum of squares. Fifth, we divide by n-1 to get the sample variance. And finally, we find the square root to get the sample standard deviation. Okay, that's a lot of steps. Let's see how we can do this on the calculator now. First, you need to enter the data into the L1 list by pressing Stat, making sure Edit is selected, then pressing Enter. Now, if you already have information in L1, you can arrow up to where L1 is highlighted and press the Clear button, and then press Enter, and then arrow back down and it'll let you enter new values. Now enter the data values, pressing Enter to progress. Next, we need to bring up the menu for one variable statistics, so you want to press Stat, then arrow over to Calc, then press Enter. At this point, your calculator may give you different options to select L1 as your list. You may have to arrow down to select it, or it may default to say L1, or you may need to press second, then 1, the number 1. After you've told the calculator you want it to use L1, or list 1, you press Enter as many times as it takes to get it to calculate. And you'll love this part. The calculator figures out all these different values because it doesn't know if you want sample or population data, so it calculates both. Make sure you know which one you're using so that you pick the right data from the display. What you're seeing on the screen now are displays from various ways you could calculate this information. You could use something called Minitab, or Excel, or the TI-84 that we just did. From the displays, from the various ways you could calculate it, you can see that the two pieces of information we're looking for, sample mean and sample standard deviation, appear. X bar, or the sample mean, is about 7.5, and lowercase s for our purposes, but capital S sub x on the calculator for sample standard deviation is about 2.15. If you use the down arrow button a few times, you see this calculator gives you the median, the min, the max, as well as some other figures we'll be going over later. This is a very powerful tool. Keep the instructions for how to access this bit handy. I know we've stated this a few times, but it's a very important concept, so I want to make sure you go away with this idea. Standard deviation is a measure of the typical amount an entry deviates from the mean. The more the entries are spread out, the greater our standard deviation. The mean and the standard deviation are two of the most important pieces of information used to describe a data set. Look at these graphs. On the first graph on the left, a mean of 5 and a standard deviation of 0 tells me that all the data entries must measure the exact same value, and they must all be stacked on the value of 5. The middle graph has the same mean as the first graph, but knowing that the standard deviation is 1.2 tells me that the data entries will be more spread out, with a little more variation away from the center. Then I compare this to the graph on the far right, and I see the mean is the same, but with slightly larger standard deviation. This tells me that the data entries will be even further spread out, which is exactly what the graph shows. Add a third layer of information, that is the shape of the distribution, like saying this graph on the right is bimodal, and you can see the entire picture in your mind's eye. Now let's apply what we've learned to a practice problem. Without calculating, can you estimate the population standard deviation of each data set below? Pause the video and see if you can come up with a reasonable value for sigma without actually plugging information into a calculator or a formula. Okay, graph number 1 is similar to a graph in a previous example. All 8 data entries are stacked on the same data value, 4, which means there's no deviation. So that means the standard deviation is 0. On graph number 2, the 8 data entries are divided perfectly in half, with 4 of the data entries stacked on the value 3 and 4 of them stacked on the data value 5. This makes the mean of the data set 4, so each group of data entries is exactly 1 unit away from the center. That is, each of the data entries has a deviation of plus or minus 1. So the population standard deviation should be 1. On graph number 3, each of the 8 entries either has a deviation of either plus or minus 1 or plus or minus 3. So you might guess that the population standard deviation would be around 2. And if you calculate it, you find that it is actually 2.2, so our estimation is not too far off. This example concludes part 1 of this section. I'd like you to take a break to absorb everything from this section. I'll see you in the second part of Section 4.